Okay, so let's have a look at these here. Okay, ideally we should have been using y equals mx plus b in order to solve these, but it is possible to have solved them using rise over run as well. Okay, we'll kind of look at both ways, but obviously y equals mx plus b is the preferable way. So if they have y equals mx plus b, give them a mark. Or if they have slope is rise over run, give them a mark. Okay, either way. We have to manipulate in order to find our slope. Okay, using y equals mx plus b, that's manipulating for m. So we subtract b over to this side and then divide by x. So give them a mark if they got to here. Okay, y minus b over x is how we solve for m. Then we need a point on the line that is at a grid intersection. You essentially have two choices there. You could use this one or this one, as they are both at grid intersections and their values are easily readable. Okay, so their next step would be they either have 1200 minus b, and b is at 0. Okay, our y-intercept here is at the origin. Okay, so 1200 minus 0 over 400, or they may have 600 minus 0 over 200, or if they did it rise over run, they probably have 1200 minus 600 over 400 minus 200. That could also, okay, if they have that, okay, you can give them a mark for that as well. Okay, that is their third mark. Okay, and then what that should come out to is $3 per unit, okay, or per whatever, okay, per quantity or whatever for on this side here. Hannah, question?
There should just put like minus b instead of minus 2, is that okay?
Yeah, that's fine. All right, now, they should have units here, guys, okay? And the units were dollars and numbers here, okay? So they should have dollars per unit, okay, or per number on this side here for units. So that's their fifth and final mark, but they do have to have the correct units. If they don't have the units, sorry, it's out of 4. Yeah, sorry. It's out of 4 marks. So if they don't have the units, they don't get the mark for the answer. I'm not worried about significant digits on this one. Okay? Because probably a lot of people forgot about that anyway. Okay? All right. Any other questions on this one? Well, for this one here, I would say that my lowest number has 3 significant figures, because 0 is infinitely accurate. If I have nothing, I'm absolutely 100% certain of it, right? Okay, so I would say it should be 3.00. Yeah. All right. For number 2, okay, same idea here. We want to use y equals mx plus b, so give them a mark if they have that. Okay, give them another mark. They manipulated it for m. What we need now are our points. Well, our y-intercept on this graph is 17.5. Okay, every line was worth, okay, is worth 2.5 on this graph. So 17.5 is our y-intercept, or b. Okay, and then finding a grid intersection, there were a couple. I think, you know, the best one is probably this one, but an argument could be made for that one there as well, or this one. If they used any of those, their values are just going to be slightly different. Okay, and it's fine. Okay, so the values I'm going to use here for y are going to be 5 and, oh, I skewed my diagram there. No, I don't know what it is. Lost my units on that one. Sorry, I gotta look back here. So at 5 and it would be 2.2. Yeah, it's 0.2 for each one. So 5 and 2.2. Okay. So give them a mark if they've got that step on there. Okay, and then our units for our slope, okay, our number should be negative 5.7. It is going down after all. Okay, degrees Celsius per hour. Right, it's telling us the rate at which this place is cooling off. 5.7 degrees Celsius per hour. Right, so that is your fourth and final mark. If they did it rise over run, okay, then they have 2 points. Okay, hopefully they were grid intersections. If they did it rise over run, they should still come up with this number. Okay, if they did it right. If they didn't do rise over run right, they didn't get this number. Okay, questions on that one? 1, 2, 3, 4. Negative 10 and 6. Yep, no, that's a legitimate point. Yep. Is it exactly 6 there? No, it's at 5. Yeah, the issue with using that one is that we can't actually see where the line goes because behind that point, it isn't actually on a grid intersection. But if they used it, we'll go with it. Yeah. If they use that point, we'll accept 5.5. But guys, listen up here. Need everyone to be quiet and listen. Okay? The issue with using this point is you can't see the grid intersection. So we don't know for sure if that's a valid grid intersection. Hannah, be quiet. Okay? So the caution here is that we've said before, you should not use points you plotted because you can't be certain of where you actually plotted them. So we'll accept it today, but it is something we need to be mindful of in the future. Okay? All right. All right, so what we're looking at today, guys, are the 2 main types of graphs that we are going to deal with in Science 10 physics. Okay? That is position versus time graphs, which we did a lab on yesterday. Okay? And velocity versus time graphs, which we haven't touched on, but we'll also be doing a lab on a little bit later. Okay, so what we have to get out of today, understand what information can be read directly from those 2 types of graphs. That's kind of the easy part. Okay? Understand that graphs and equations from kinematics show the same information in different ways. Okay, so basically, how can we calculate stuff from the graphs that we might make, okay, in this course? And how do those relate to the formulas that are on our formula sheet? Right? And the last thing, okay, learn that kinematics equations are actually derived from graphs. And you're going to see that several of the equations that are on your formula sheet are actually slope calculations from a certain type of graph. Okay? All right. One of the things we have to be able to do in this course with a graph is be able to take one look at it and say, here's what's happening in that graph, qualitatively. Okay? That means without any numbers. So I need to be able to look at this graph here on the left and say that in this first part here, the object is not moving. Right? How do I know, looking at that position versus time graph, that in the first second of movement, that this object doesn't actually move? It stays in the same spot, right? Okay? Its position at time 0 was 20 meters. Its position at time 1 second is 20 meters. Didn't go anywhere. Okay? Its position is unchanged, therefore it isn't moving. Right? But I've got to be able to look at that in a snapshot and go, okay, here's what's going on. Right? What's going on between time 1 second and time 3 seconds? It is moving. How is it moving? What is it increasing? It's increasing its position, right? It's not, but a lot of times we look at this and we go, it's accelerating. Okay? A lot of people think that when they first look at that graph, they go, that object's accelerating because they see a line going up. But in actual fact, this object is traveling at a constant velocity right now, because in the first second, it goes 20 meters. And in the next second, it also goes 20 meters. Okay? That's an object traveling at a constant velocity. Okay? A diagonal line is an object traveling at a constant velocity on a position versus time graph. The steeper the line, the faster it's going. Okay? And that would seem to make sense. The steeper it is, the farther it goes in every time interval. Everybody all right with that? Okay. What's it doing here? Not moving. It's, yeah, okay. What about here? It's going backwards. It's decreasing its position. It's going back. Same thing, right? I'm moving from position 60 meters back to position 20 meters. Well, the only way to do that is to go backwards. Okay? So this is showing an object moving backwards, again, at a constant velocity. Okay? Everybody with me there? All right. If I'm accelerating, obviously my velocity is changing. Okay? If my velocity is changing, what happens to the distance I travel every second? Right. Not only does my position change, but how far I go each second gets bigger as well. All right? That's what this graph on the right is showing. Okay? A position versus time graph of an accelerating object makes a curve. Because in the first second, I only went maybe a meter or so, not very far. Okay? But I kept accelerating. I kept going faster and faster. So in the next second, I traveled quite a bit further. You can see the distance here is very small. This distance is quite a bit bigger. And in the next second, it's even longer and longer and longer. I'm traveling farther each second than I did the second before. I'm not traveling the same distance every second. Everybody follow there? Right? So those are patterns we've got to be able to recognize right away. Okay? See them and go, all right, that means that this is doing this. Right? I can't remember the last time I didn't have a question on the unit exam or final that went like this. Using the position versus time graph in this question, tell me what's going on in section A, B, C, and D. No math, just tell me what's happening. All right? So I've got to be able to look at that graph and say, in part A, the object's position is not changing, therefore it is standing still. Okay? In part B, the object's position is changing in a positive direction. It is traveling at a constant velocity forwards. Okay? Part C, not moving. Okay? Part D, position is changing in a negative direction. The object is moving backwards at a constant velocity. Okay? That would be the level of detail that would be required for a question like that. If you just said, moving forwards, okay, that's partially true, but not good enough to get you full marks because there's lots of different ways to move forwards. That you could accelerate forwards, okay, you could move forwards at a constant velocity. You have to be specific. Making sense? All right. So position time graphs are used to represent the location of a moving object over the course of time, okay? And so we can read displacement right off of these graphs. On your formula sheet is this formula. Displacement is final position minus initial position. Okay? Because obviously that's what displacement finds, is your change, how far and in what direction you have gone. In other words, your change in position. So for this graph right here, the first one on the left, what is the displacement of the object over the whole trip? It's 0. Okay? Because the final position is 20 meters, and the initial position is 20 meters, and 20 minus 20 is 0. It didn't go anywhere. It came back to where it started. Right? If I asked you what's the displacement of the object between time 1 second and 3 seconds, what's it going to be? 40 meters, 40 meters forwards. Remember, or positive 40 meters, okay? Because it's a vector quantity, right? Displacement's a vector quantity, so we would need to have that positive 40 meters forward, something like that. Similar thing, if I asked you what's the displacement between here and here, okay, you would go final position, 20, minus initial position, 60, and you're going to get negative 40 meters, or 40 meters backwards, okay? Something like that. Is that a very difficult calculation? Nope. Okay, it isn't. Okay. Now, slope calculations, we've already talked about those. Okay, you can do rise over run, okay? But what we're trying to illustrate here is something else, not actually that. Okay, if I have a position versus time graph that's showing a line that goes like this, okay, when I calculate the slope of that line, I'm dividing the change in y, which is in meters, by the change in x, which is in seconds. So what do I get when I divide the change in displacement by the change in time? Velocity, right? Okay. V equals d over t is derived from a position versus time graph. It's final position minus initial position over time. In other words, it's y minus b over x. Okay, good. Sometimes I get that aha moment. It doesn't, I mean, not everyone, but okay, I do get it often, and that's good. Okay, that's where that formula comes from, guys. It's just displacement over time as long as you've got that line there. Okay, so that's calculated from the slope of the line on your velocity, on your position versus time graph. Okay. All right. Here's a typical question that you could get on maybe like a quiz or even on a unit exam. Okay, I give you this graph and I ask you, first off, what's the object doing in part A? Okay, now we have to be mindful of how we word that. I'm hearing a lot of correct stuff, but I'm hearing it interspersed with things that are misleading. Okay, if I say increasing at a constant velocity, I need to indicate what am I increasing. I'm increasing my displacement or something like that. I would say the best answer for part A would just be moving forwards at a constant velocity. Okay, that indicates positions changing, and here's how. All right, at a constant rate, kind of. Okay, for part B, we're looking at an object that's not moving, right? Its position is unchanged. Okay, in part C, moving backwards at a constant velocity, right? Okay, and for part D, stationary. Part E, at forwards at a constant velocity. And what about F? At again, a constant velocity. Where is it going faster, E or F? E. E is steeper. Okay, it's traveling, and it's increasing its position more in part E than it does in part F in a shorter space of time. All right, let's say I asked you to calculate the average velocity of the object over the whole trip. It is actually. What is it? Right. Yeah, there's no displacement, right? We started at position 0, and we ended at position 0. Okay? The only thing that's changed is time. I ended up back where I started, so I didn't really accomplish anything. Okay? V equals displacement over time, and as Nick pointed out, the displacement is 0, so my velocity has to be 0. Okay, so that part, that's easy because, like we said, there's no displacement, so the math ends up being fairly simple on one like that. Okay? What if I asked you to calculate the average velocity between the start and 10 seconds? Right. I would use the one for velocity. I can't use slope here because look at my graph, right? In this case, I can't use these lines. They're all different. Now, really what I am doing is drawing an imaginary line there and finding its slope using, right? I'm imagining there's a straight line from one place to the next, and I'm finding its slope by essentially going final position minus initial position divided by time. Okay, what's my final position? Negative 10 meters. Okay, my initial position is 0, and that took 10 seconds. Well, look at that. What my average velocity is? Negative 1 meter per second. Okay, so really, all we've done so far is some of those problems that we did that were in word form. Now we're doing it with a graph instead. Okay, that's why we did V equals D over T first, so that when we got to graphs, you'd be familiar with the math. Okay? The graphs, it's actually a little bit easier because you're not having to read it and then turn it into math. You got it right away. Okay? A graph is a little easier to read oftentimes than a big long problem with lots of words. Okay? All right. So for things like vector quantities, that's fairly straightforward. What actually becomes a little more involved, not harder, but more involved, is when you're having to find scalar quantities from a graph. So let's say I wanted you to tell me the total distance traveled over this whole trip. How are you going to find that? Yes, that's exactly what you do. You just add it all up. Okay? Remember, direction doesn't matter for distance. It's scalar. So how far does it go here? 6 meters. How far does it go here? Nothing. Okay? And it goes from 6 to minus 10. So that's 16. This is 0. Okay? This goes from 10 to 4, so it's 6, and this is 4. All right, so now I know how long, distance-wise, each line. Sorry, I'm getting some weird looks. Did you guys not see how I did that? Okay? So here's what I did, right? I went from 0 to 6. So this line is 6 long, right? This line here ended at minus 10 and started at positive 6. So like this was 6 and this was 10. The whole thing was 16. Everybody okay with that? And then this went from minus 10 to minus 4. That's 6. And there was 4 left back to 0. So I add it all together, okay? Which comes out to 32 meters. Okay. Now, assuming this whole trip takes, let's say it takes 17 seconds. Let's say that's where it ended up. How fast is the object going? Nope. I can divide. What two things am I dividing? 32 over 17, right. I'm going to go distance over time. Okay, same formula we've been using. Nothing new, nothing difficult there. Okay, we know how to do that. We just have to get some of the numbers off the graph rather than drawing out the part 1, part 2, part 3 like we did in the multi-step questions before. Okay. All right. So I would expect, guys, that you should expect, I should say, to see something like that on a quiz or a unit exam, okay, that I would ask you to do those kinds of calculations using a graph. Okay? So that's the stuff we can calculate from a position versus time graph. We can calculate displacement using final position minus initial position. We can calculate velocity either by calculating the slope if we only have one line on the graph, or by using v equals d over t. All right? Making sense there? Okay, velocity versus time graphs are a little bit more involved. We haven't talked about those yet, so that'll be a little bit new. Now, before we get to velocity versus time graphs, what's going on this graph? Yeah, there's accelerations, decelerations, accelerations that are backwards, okay, all of that kind of stuff. In physics, true physicists don't use the term decelerate, okay? An acceleration is any change in velocity. A negative acceleration could mean slowing down or accelerating backwards, which is the same thing, okay? Believe it or not, when you slow down, you do that by exerting a force backwards, right? So if I'm running and I want to slow down, I start catching my toes in and leaning back and doing things that actually exert a force in a backwards direction that slow me down. When you apply the brakes on your car, believe it or not, that actually exerts a force backwards. Okay? It squeezes the brakes and friction acts backwards. Okay? And so as a result, your car slows down. Now, if this object is accelerating, like it is here in part A, its velocity is always changing. So I can't find the slope of a curve, can I? Right? Normally we would say if I want to find the velocity, let's say right here at this point, there's no way for me to do that using this value here and this value here. Okay? Because if I find that, what I'm saying is that there's a straight line that exists between those two. Well, the slope of that line is the average velocity between here and there, not the instantaneous velocity at this point here. Okay? Those are going to be different numbers. So, in order to do that, I have to explain to you the only thing I understood in university calculus. Okay? That was the first day. After that, I didn't understand anything. Okay? I got through university calculus by memorizing the examples in the textbook and writing them down on my final exam and getting part marks for method. I kid you not. Okay? Luckily, the class average on my calculus final exam was 39%. Luckily, I know, that's where the story takes a turn. Luckily, the average was 39%, and I got 41. Okay? Which means, in university, since you get graded on the curve, as long as you do better than a certain number of people in the class, you pass. So I did. We call that in university lingo, surfing the curve. Okay? Yeah. That's because that's exactly what you do. You surf the top part of the curve and you pass. Okay? I surfed the curve lots in university. Chemistry, same thing. Okay? Organic chem, class average 37%. Me, 39. I passed. Okay? Yeah. I know it doesn't seem like I passed, but I did. Okay? So, I'm going to explain to you guys the only thing I understood day one of university calculus. Okay? So, a mathematician looks at a curve and they don't see a curve. They see an infinitely large number of infinitely small straight lines strung together at ever-increasing angles. It would be like if you looked at two pictures on the internet of the same thing, one in low resolution and one in high resolution. Okay? In the high resolution picture, the edges are all smooth because the pixels are really, really small. In the low resolution picture, you see all the pixels. You see all the little boxes. Okay? Well, when a mathematician looks at a curve, they see the boxes. They see the little lines that are changing angles that make up this curve. Okay? Everybody with me so far? Like I said, that was the only thing I understood. After that, it was the limit of 0 is this or something, and it didn't make any sense. Okay? So, if there's a whole bunch of little tiny lines, all I need to do is find the slope of the little tiny line that exists right here at point A. So, the problem is that line's really, really small. And I'm not going to be able to know what B is or get a Y or an X value or a grid intersection. That's going to be problematic. But there's a trick. There's a trick. How many people have heard of the term tangent line? Okay. A tangent is a line that touches a curve at a certain point but never crosses it. In other words, it's parallel to the curve at that spot. So if I draw a tangent line that's parallel to the curve, I'm going to have to adjust that a little bit. It's a little bit too steep, I think. Okay? I now have a line with exactly the same slope as that little line I couldn't see, and it's long enough I can calculate the slope of it now. Okay? Everybody with me there? You're not going to be asked to do that hardly at all, like ever. Okay? But it's important that you know that that can happen. Okay? So, if I found the slope of this line, which I could because I got a grid intersection here and here, right? I could use slope as rise over run. I don't know what B is because it's outside the range of my graph, okay? But I could use rise over run with these 2 points and know how fast I was going now at point A. All right? Okay, so in the first part of this graph, the object is obviously speeding up because it's getting steeper, right? This curve is getting steeper, so all those infinitely small lines, their slopes are getting larger and larger. All right, but what's happening here as we go kind of around this point B? Okay, so right here we're increasing speed, but now what happens to this curve? It actually, the slope kind of changes. Now it's flattening. It is. It's slowing down here. Okay? It's slowing down, but then immediately after the slowdown, what does it start to do? It starts to accelerate the other direction. This is actually a graph of this. Okay? During the first part, I'm throwing this thing up in the air. I'm accelerating it with my hand. That's part A. Once it leaves my hand, the only thing affecting it is gravity, which is pulling it back down to the earth. In other words, slowing it down, stopping it, and then bringing it back to earth. Okay? Now, how do I know it stops? Okay, it won't go any higher. It's changing direction. And if I drew a tangent line that touched B, whoa. It would have a slope of 0. Okay, that object is obviously stopping for an instant, at least, okay, at the top of its flight while it changes direction. Okay, what goes up must come down. That's the graph of that. Okay, and then right here in part C, you can see that the graph starts to get flat again here at the bottom because that's where I catch the marker and slow it down again. All right. So that's the kind of interpretation that you'll need to be able to do. I show you a graph and you tell me, you know, maybe this is a multiple choice question and I ask, which of the following situations is probably being shown by this graph? A, object, car on cruise control traveling down the highway. Okay. B, object thrown up into the air and then caught. Okay. C, bird flying through the air. Okay. Or D, falling object dropped from the top of a building. Okay. It isn't any of those, right? Except for, sorry, the second one, sorry. Yeah, throwing it up in the air and catching it. So that's the kind of analysis or interpretation that you're going to be required to do when given a graph. Okay? Rarely are you ever going to be asked to do the math of calculate the instantaneous velocity, but it's important that you see how that affects it here. All right. Now, velocity versus time graphs. So what does the velocity versus time graph show us? Exactly what it says. It shows the object's velocity over the course of time. Okay? So you could have a velocity versus time graph and a position versus time graph side by side of the same object, and they're going to look different, even though it's the same motion being graphed, because they're looking at it from two different perspectives. Okay? So here's a position time graph. What is it showing? Is it accelerating? It's traveling at? All right, its position is changing at a constant rate. In other words, it's traveling at a constant velocity. Yeah, okay? We could say constant speed, but constant velocity is more accurate, okay? Because we know it's moving forwards, okay? So it's traveling at a constant velocity here, okay? It's moving in a forward direction. This is a velocity versus time graph. What is it showing? Something traveling at a constant velocity, right? Its velocity is staying the same, right? But our instinct right away is to look at that and go, but that's not changing, so it's stopped. Well, it's stopped if it's a position time graph and it looks like that. But now it's a velocity versus time graph. Okay? Now it's showing that the speed of this object, the velocity of this object is unchanged as it travels along. In fact, these two graphs are of exactly the same object. Okay? So let's say I want to prove that. Right? Looking at this graph here, it looks like the velocity it's traveling at is about 260. Right? It's a little more than 250. Right? About 260 meters per second. Everyone okay with that? Okay. How can I prove that this graph here is of the same motion? Okay. I mean, yeah, I could look at the times. They are the same, but that could just be coincidence. Okay. Can I calculate something from the position versus time graph? Yeah, if I calculate the slope, what is it going to tell me? Okay, I'm hearing some of the right answers. Remember, when I find the slope of this, I'm going to be finding the change in position divided by the change in time, which equals, right, if I find the slope of this line, it should be this number. Agreed? That way I'll know they're the same graph. So, okay, my final position on this graph is 1400. Okay, my initial position on this graph is 100. Okay, and my time is 5 seconds. Well, pretty sure that 1300 over 5 is 260 meters per second. Okay? Everybody all right with that? Okay, so this velocity versus time graph is showing something traveling at a constant velocity. What's that graph showing? It's showing what? Acceleration. Okay? Carson, Brandon. Okay. How do I know it's showing acceleration? What is that line saying is happening? The velocity is changing. In this case, it's increasing. Right? That's a positive acceleration. This object is going faster and faster and faster. Okay? If I had, whoops. Sometimes smartboards don't work well. All right, what's that object doing? It's slowing down, right? And in fact, it's coming, oh no, I don't have 0 on there. Okay, if my bottom line was 0, then I could say that it was actually coming to a stop. Okay, in this case, I can only say it's slowing down because I don't know if it actually stops or not according to my graph. Okay. All right. Something we haven't talked about yet is acceleration. Okay, we'll be getting to that after we talk about graphs. But what acceleration really is any change in velocity. You might want to write that down. Over time. Okay, acceleration is any change in velocity over time. Now, on your formula sheet, you've probably seen this symbol next to a few things. it does not indicate that you should use a triangle to manipulate that formula in any way. Okay? I had one person tell me that one time. Okay? What this triangle means is change. It's the Greek letter delta, and delta means change in science. Anytime you see delta something, it means final minus initial. So you see it in your velocity formula. It says delta d over delta t, which basically means final position minus initial position over final time minus initial time, or displacement over time. Okay? You also have a formula on there that looks like this. Acceleration is delta, didn't draw that triangle very well. Delta V over delta T. And then it's written, I think, like this next to that. Okay? So acceleration is the change in velocity. So VF, sorry, these should have arrows. VF minus VI divided by T. Okay? That's how we calculate acceleration. Does anyone need that anymore? Okay, so let's say that we've got this graph, and it asks me, calculate the acceleration of the object over the whole trip. Okay, well, we just saw that we have an acceleration formula that looks like this. What's on my y-axis? Velocity, right? What's on my x-axis? Time. Okay, so if I'm taking this point here, my final velocity, and this point here, which also happens to be my y-intercept, it's not the origin because it starts at 100, right? Okay, but that's my y-intercept, okay? Am I really just going again? Just like I was with the position versus time graph, I'm calculating now the rate of change of velocity instead of the rate of change of position like I was in the last graph. Okay? Now, the reason I keep showing you this, and I know it's the same thing as the position time graph, is we don't want people to get in the habit of memorizing what they can get from a certain kind of graph. That might get you through Science 10 physics, where we only have 2 or 3 graphs. Okay? But you get to Physics 20, and you're going to be dealing with at least a dozen different graphs. You get to Physics 30, and that number is easily 40 different graphs. You cannot memorize every graph and what you can get off of it. But if you can remember, y equals mx plus b, you can interpret what you might be able to get off of a graph instead. Okay? And it's easier to have that one skill and apply it to many graphs than memorize 40 graphs. Or if I didn't have the line, like let's say there are points all over the place, I wouldn't necessarily draw a line. I'd say, okay, well, there's my final, there's my initial. I have this imaginary line that is now representing the average over the whole trip. Yeah? Okay, so for this, each line here is worth 50, right? So we got 450, 5. So our final is 550, so that'll be y. Okay, minus b, which is 100. And the whole trip takes 7.5 seconds. Okay, so we got 450 over 7.5. All right, so the acceleration of this object is 60, but what are my units? Meters per second are the units for velocity. I'm changing my velocity. So I'm showing the rate at which I change my velocity. Meters per second, okay? Which we usually abbreviate as this. Meters per second squared, okay? Those are your units for acceleration. That's where the acceleration formula we're going to be using next week comes from. It's the slope of a line on a velocity versus time graph. Okay. Anybody need that part? I got to take it off. All right, so let's move this line out of here. All right, so let's go back to this situation here. What if I have that velocity versus time graph that shows an object traveling at a constant speed or constant velocity, and it asks me, using this graph, calculate the displacement of the object over the whole trip. I didn't either. Can't I just what, Hannah? Yes. Okay. I can use, so Hannah's suggestion here is, can't you just use v equals d over t? And the answer is yes, I can, because this object is traveling at a constant velocity. So what I'm going to do, okay, listening guys, okay, is I'm going to manipulate v equals d over t for d. So I'm going to multiply both sides by t, and now I've got it set up. So really, I'm taking this and multiplying it by this. In other words, I'm calculating the area underneath this line, this rectangle. Okay? Now, just to make sure that I'm actually calculating what I think I'm calculating, okay, I'm going to take my 260 meters per second and multiply that by 5 seconds. Okay, what's going to happen to the seconds? They're going to cancel out, and I'm going to be left with meters. 1,300 of them to be exact, which is exactly what this graph says my displacement was. 1,400 minus 100 is 1,300. Okay? Now, here's the thing we got to remember about this formula. I didn't write it in here, but this is calculating the average velocity. Now, we know the velocity didn't change in that graph, but we still have to treat it that way. That was the average velocity over the whole trip. Okay, so now I want to calculate the total displacement over the whole trip for that line. Can I still use v equals d over t even though this is now showing an object whose speed is changing? Actually, I can if I cheat a little. Okay? When we calculated the displacement that this object had traveled, we calculated the area underneath the line by multiplying the average velocity by time. Right? I can still do that for this object. I just have to know what its average velocity is. Well, it's changing from 100 to 550. So that means that the halfway point between those two marks would be the average. Half the time I'd be going slower than that, and half the time I'd be going faster than that. Everybody all right with that? Okay. And then I'd have to multiply that by the time, right? I'm still doing average velocity multiplied by time equals displacement. What do I do to get the average velocity, though? We said it's the halfway point on this axis. So what do I do to find that? Yeah, but how do I find the halfway point? I take the height of this graph and divide it by 2, exactly. I divide it by 2, right? It's the halfway point. So I take the height of my graph, which is 450, because it starts at 100, and I divide that by 2. Because it goes from 100 to 550. So the height of this graph is 450. Yeah? Okay, so here's what I just did. I said this is the height divided by 2 times the base. Is that how you calculate the area of a triangle? Yeah, base times height over 2. No, that's how you calculate the hypotenuse. Okay, so if we calculate the area underneath this line, or the area underneath any line, on a velocity versus time graph, we're going to find the displacement of the object. Okay, because we're taking the average velocity and multiplying it by time for each section of the graph. Okay, so in this case then, we would have 450 over 2, which is 225 times 7.5. Okay, 225 times 7.5, I don't know what that comes out to, but okay, that's how we would calculate the total displacement in that graph. Okay, we're not really changing anything, it's still average velocity times time. We're cheating a little bit here. Okay, the object is accelerating, its velocity is changing, but we're using the average to help us out. As long as there aren't a whole bunch of different sections, we can do that. Okay. Looking at this graph here, what is this person doing? For part of the graph, he's accelerating. Is he stopping? He's staying at a constant speed, right? It's a velocity versus time graph. Here, his velocity is changing. Here, it's staying pretty much constant, and here, he's stopping. Okay? He does get all the way back down to 0, so he comes to a stop. So this is a race. Here's the acceleration part of the race. Once you reach your top speed, you maintain it until you reach the finish line, where you slow down and come to a stop. Okay? Again, that's the kind of thing that you could expect to see. Here's a graph. Which of the following situations is it showing? Okay? All right, and this is what I just showed you here a minute ago, all that slope stuff. But I kept my chicken scratch from another time, I guess. Okay, but we've already gone over that. Okay, so what can we get from a velocity versus time graph? Well, we can read the velocity of the object at any point in time. That's directly off the graph. Okay, we can calculate the acceleration using the slope. Okay, which equals y minus b over x, or vf minus vi over t. Okay, and we can calculate the area under the line, okay, to calculate the displacement, because that's taking average velocity times time equals displacement. Okay, those are the calculations that we can do from a velocity versus time graph. Those are the things you will be required to do. Okay, so expect that on a unit exam, you're going to have several graphs. Okay, like several in the multiple choice, and then probably one of each in the written. One that's velocity versus time, one that's position versus time. Expect to be asked to do these same kinds of calculations on those graphs. Okay. Questions there? All right. I'm going to make a copy of this sheet for you guys. I forgot to do it. I didn't think we would get this far. Okay. Just have a look at this one here, and you can get started on it right now, okay, while I photocopy that for you.